Rajeshwari MJ. She pursued her BE in Electrical and Electronics at the People's Education Society College of Engineering, Mandya. She pursued her MTech in VLSI Design and Embedded Systems at the Sri Jagadguru Balagangadharanta Institute of Technology, Bangalore. Her personal skills lie in good verbal and written communication skills. Her areas of interest lie in OOPS with C++, renewable energy sources, HVDC transmission, digital relays, automotive electronics, advances in VLSI design. She has also had papers presented at the national level, such as the Innovative Architecture for SoC Multi-Core Hybrid Processor, presented at the RNSIT, Bangalore.
Welcome to UGC lecture series of BSc Physics Honors. Today we are dealing with the subject electronic devices. In this session we are going to concentrate on amplifiers. So some of the topics that we are going to cover in the amplifier section are transistor biasing, stabilization circuits, fixed bias and voltage divider bias. These are the two types of biasing circuits that will be used in a transistor for biasing purpose. So in the previous session and all we discussed about biasing. The term biasing in the sense giving the external DC voltage to the transistor. It has to operate in a linear region. So how we are going to bias a transistor and what are the different methods that we are going to use for a transistor to behave as an amplifier, that is it has to work in a active region, so that we can say that the transistor is working as an amplifier. So very first things that we need to know about is biasing of BHAT. So the term is already said is biasing refers to the application of DC voltages to set up the operating point in such a way that output signal is undistorted throughout the whole operation. So throughout the whole operation the output signal should not be distorted. That is the main theme that hidden behind of biasing a transistor. So whatever the external DC supply we are going to give, that DC supply should not distort the output signal. So also we need to know about the faithful amplification. So amplifiers, that what we are studying in this section means amplification has to be done with the help of circuit. So circuit will always give the faithful amplification. So this faithful amplification in the sense the output signal should not have any distorted signal. So the output amplification shape, the shape of the output signal should not be disturbed, and it is same, the shape of the output will be matches with the input signal shape. So that is called as faithful amplification. So these are the things that we need to know about the amplifier. So we know what will be the input signal, but output signal should not distorted and should not have any change in the shape of the input signal. That is called as faithful amplification. And also biasing in the sense the DC supply voltage that we are going to give, it should not distort the output signal. So this is how we are going to choose a biasing circuit which will helpful for an better amplification. So also once selected properly, that is once that we are going to select a biasing circuit properly, the Q point should not shift because of change of IC. So once we have already chosen a biasing a DC external voltage means that should not affect or that should not affect on the Q point or operating point or quiescent point, that what we said. Q point it should not operate because the Q point should always depend on IC, that is collector current, and also due to this collector current may change if we change the biasing voltage. So that is why this indirectly depends also on Q point. That is why it is very important to choose a best biasing voltage, so that it has to operate to give a output with the undistorted output. So, what are the things that will going to cause a change in IC? Because beta variation due to replacement of the transistor of same type. So, these are the two things, that is beta variation in the sense that also gives rise to change in the collector current, and also temperature variation. Another things that will change the collector current is temperature variation also affects the collector current. So, these are the two things that we need to remember when we are going to speak about the biasing of a transistor. These two things that we need to keep about a circuit or method that we are going to choose for a transistor biasing. Next, another term that is not at all heard before, that is stabilization. The process of making operating point independent of temperature changes or variation in transistor parameter is known as stabilization. So, how we are going to make this stabilization is we will study further in the next upcoming slides. And now, how this stabilization of operating point is necessary because temperature dependence of IC. So, stabilization is related with the temperature, we know with the definition. So, as IC also dependent, that is collector current also depend on the temperature. So, the stabilization is necessary due to because of the temperature dependence of IC and also individual variations and also thermal runaway. These are the three reasons that why we need a stabilization. Next, stabilization, temperature dependence of IC and thermal runaway is a reason that why we need a stabilization. So, with the help of this formula we can able to know how the stabilization is dependent on IC. So, IC formula is equal to beta into IB plus beta plus into ICBO, that is leakage current. So, ICBO is strong function of temperature, even though it is very small, but it is strongly dependent on temperature. So, temperature affects more on ICBO, that is leakage current. So, a rise of 10 degrees centigrade doubles this ICBO and IC will increases because beta plus 1 times of ICBO is there. If for a 20 degrees centigrade change in temperature, which may leads to change in the ICBO, which in turns increases the collector current. So, the flow of IC produces heat within the transistor and raises the transistor temperature further, and therefore, further increase in ICBO. So, this may cause an increase in temperature, and also the temperature increases in the sense again it leads to the increase of ICBO. So, this leads to again the collector current also increases. This effect is cumulative, and in few seconds the IC may become large enough to burn out the transistor. So, the IC should be in minimal ways in such way that it should not burn out the transistor. Because of this increase in temperature which leads to increase in ICBO, and therefore, it increases the collector current. So, the transistor may damage due to high collector current. And also this self destruction of an unstabilized transistor is known as thermal runaway, because of this high temperature which may leads to destruction of transistor. This is called as a thermal runaway. So, next we need to know about the stability factor. So, this stability factor mainly helps in how we are going to stabilize a transistor with this factor, and how this stability factor should be lies in a which value makes the transistor to be in a stabilized condition. So, the rate of change collector current IC with respect to the collector leakage current ICBO is called stability factor. So, the S is ratio of IC and DC, but the rate of change of IC to the rate of change of ICBO. From in this expression that we can say that lower the value of S, better the stability of the transistor. So, we need to always keep in mind that the stability factor should be low, so that we can have a transistor with a better stabilized condition. So, transistor can be in a stabilized condition when the S value will be of lower. So, the rate of change of collector current IC with respect to the collector leakage current ICBO at constant beta and IB is called stability factor. That is also we can say it is denoted by this by S, and also the IC is always equal to, that IC is equal to beta into IB plus beta plus 1 into ICBO. The same thing that we are repeated here, because we need to keep in mind that it also that there is a constant, that is current gain factor, that is also multiplied by ICVO. That is also we need to consider when we are speaking about stability factor. So, IC is equal to beta plus beta into IB plus beta plus 1 into ICBO. This is the equation that we get. So, we are differentiating this equation with respect to IC, which will give this, and also by rearranging for yes, because after differentiating this equation by IC, we will get ICBO divided by IC, which we can rearrange this and we can get the value of S here, because the reciprocal of this will give the value of S. So, here we replace the S here. So, after that we will get the value of S. So, for getting the value of X, S will be equal to beta plus 1 divided by 1 minus of beta into differentiation of IB with respect to IC is what the stability factor. So, this is in related with a collector current, we will get the stability factor, and also we need to know that stability factor should always be lower for better performance, and we can say that transistor will be stabilized when the stability factor is in low, it is if it is having a lower value. So, next we move on to different types of biasing circuits that we are going to study here. We are going to study the two types of biasing circuits are fixed bias or base resistor biasing, and also voltage divider bias. These are the two biasing schemes or methods that we are going to study. So, firstly that fixed bias, the name itself said fixed bias or base resistor bias. So, that is base resistor is going to helpful for maintaining the bias voltage. So, how it is going to helpful? Let us see with the arrangements of circuit. This form of biasing is also called as base bias. The single power is used for both collector and as well as base. Here we can observe this is the emitter we are considered throughout in this session for discussion, the common emitter mode. So, for the base and collector we are using the common supply here. So, this is a first thing that we need to know for a fixed bias, and although we can separately also we can use commonly also for a base and collector. And for this circuit, if we apply the KVL in the base emitter loop, in the base and emitter loop, if we apply like this, for this loop if we apply KVL, what will be the value that we get? That is VCC minus RB into IB. This is VCC minus RB into IB, and minus VBE is equal to 0. That is what the KVL for base to emitter loop. And also the for getting a IB, that is current IB value with this expression, we get the IB is equal to VCC minus VBE divided by RB is what the base current we got from this KVL expression. So, after that again if we want IC is, we know the expression for IC, that is IC is equal to beta times of IB. So, IB value we already got from above expression, that is IB is equal to VCC minus VBE divided by RB. This value is substituted here. So, this IC value becomes this, that is beta into VCC minus VBE divided by RB. So, this keep in mind, and next again we apply for the another loop we are going to apply the KVL. So, that is this loop that we are going to apply from collector to emitter loop, that we are going to apply the KVL here. So, for collector to emitter if we apply, it comes like this, from VCC minus IC into RC minus VCE, that is equal to 0 is what the expression for this loop. So, here VCE, that is the collector to emitter voltage, is equal to VCC minus IC into RC. So, these are the two things that we need to know for getting a Q point. So, that is a collector output output voltage and input current, which will going to gives which will going to helpful for IB, which will going to helpful for finding the current, that is output current IC also we got, and output voltage also we got. So, from output current and output voltage we can able to set the operating point or Q point. So, QVC IC will be set with this expression. So, this is how with the help of applying a resistor KVL for the two loops, that is emitter base and also emitter collector loop, we can able to find the collector current and also output voltage, that is collector voltage and the collector current. By knowing these two values we can set the operating point. So, what are the advantages of fixed bias here? The advantages is operating point can be shifted easily whenever in the active region by merely changing the base resistor RB. So, by changing the base resistor RB we can merely change the operating point, that is the flexibility that we can have in this type of fixed bias configuration when we are using for a biasing purpose. So, by changing the RB resistor we can able to change the Q point. So, this is a flexibility that we can have with the using fixed bias as a transistor biasing circuit, and also a very small number of components are required here for biasing purpose. And also the disadvantage is also there, that is poor stabilization will be there and high stability factor, that is S is equal to beta plus 1 will be what, because IB is constant. Here IB is always constant, that is why we, from the expression we know that dB that is dB divided by DIC is equal to 0, in the sense S is equal to beta plus 1. We can go back and we can check. So, here if it is IB is constant and if this becomes 0, in the sense beta plus 1 is what the stability factor, that is why S is equal to beta plus 1 is what the stability factor when we are using fixed bias circuit. So, this will leads to a high stability factor, which should not we expect. The stability factor always should be lower for better stabilization, that is S should be always lower, but here it is higher. So, it prone to thermal runaway. Next, where we are actually, even though we are going to use this type of fixed bias circuit somewhere. So, due to the above inherent drawbacks, fixed bias is rarely used in linear circuits. So, linear circuits we are not able to use because it is having high stability factor, but we are going to use this type of circuits in logic gates whenever it is needed for transistor to operate as a logic gate. In that situation, for that application we are going to use as fixed bias circuits. Next, we move on to another type of biasing scheme, that is voltage divider bias. So, this is the most widely used method to provide biasing and the stabilization of a transistor. So, in this method, as the name says, voltage divider, in the sense we are going to divide the voltage with the respect to resistor. So, in this form, biasing R1 and R2 divide the supply voltage VCC and voltage across R2 provide fixed bias voltage, that is VB at the transistor base. This will be going to give a fixed bias voltage, and R1 will actually R1 and R2 divide the VCC equally. So, R2 is what helps in maintaining the fixed bias voltage VB at the transistor base. And also we need to know a resistor RE is included in series with the emitter that provides the stabilization. So, this RE is actually helps for the stabilization, and R2 is leads for the fixed bias, and R1 and R2 is what which is making a voltage dividing equally here. So, this is how that circuit arrangement for voltage divider bias. So, if we consider this circuit separately, and this is voltage across R2, that is what we needed, that that is VB is a base voltage, that is voltage across R2 is the base voltage. So, VB is equal to voltage across R2, that is ignoring base current here, we will find that VB is equal to VCC into R2 divided by R1 plus R2 is what we get the base voltage with respect to voltage divider formula. When we are use the voltage divider formula or method here to find the base voltage, this is how we can find the base voltage, that is VB is equal to VCC into R2 divided by R1 plus R2 is what we know that this R1 and R2 is dividing equally the supply voltage. So, also we know that with the help of this circuit we can able to make this as a Thevenin equivalent resistor. So, if we make this as a Thevenin equivalent resistor, this is how it comes. VB is a base voltage, that is VTH, we can make it as that is equal to VCC into R2 divided by R1 plus R2 is what we know. And if you want the Thevenin equivalent circuit, since R1 is parallel to R2, so this will comes to the this formula, that is R1 into R2 divided by R1 plus R2. So, this value we already know, and now we comes to the loop and we find the different current voltages. We apply the KVL for different loops and find the current and voltage for getting a Q point. So, VTH minus this is the voltage that is here, that is from base and emitter loop. If we consider from base and emitter loop, VTH minus IB into RTH minus VBE E minus beta plus 1 into IB into RE is what the expression that we got from this loop, that is from emitter to base to emitter loop, and that is equal to 0. So, from this expression we can easily find the base current, that is base current is equal to VTH minus VBE divided by RTH plus beta plus 1 into RE. So, if we consider the collector to emitter loop, here also we can able to find the collector current IC is equal to beta into IB is what the expression that we will get for a common emitter type of transistor. So, IB value we already know. So, IB value we are substituting this IB value here, that is beta times of this, and also with the KVL if we apply for collector to emitter, VC is equal to VC IC into VCC in minus of IC into RC, and here if comes minus RE IE into RE, that is equal to VCC minus IC into RC minus IE is always we know that IE is equal to IC plus IB, that we substitute here for the IE value, that into RE. So, this is expression that we got from KVL, applying KVL for collector to emitter loop. So, for bias stabilization, that important points that we need to know is that the Thevenin resistor is always very much lesser than the Thevenin resistor should always very much lesser than beta plus 1 into RE. So, this is very much lesser than beta plus 1 into RE. So, IC this we can this is what this RTH we can neglect here. So, beta plus 1 RE is very much greater than RTH. So, this beta plus 1 into RE is what we get. So, after that if we use this we will get VTH minus VBI divided by RE is what the expression that we get for a IC. IC is approximately equal to VTH minus VBE divided by RE. So, also for stability factor that we are when we consider for a voltage divider bias, it looks like this, the same expression that we already discussed for the fixed bias also. S is equal to beta plus 1, that is divided by 1 minus beta into DIB divided by DIC. So, with the help of KVL we got this expression, that is VTH minus IB into RTH minus VB. This is the expression that we got. From this, if we apply IE value as IB plus IC, this expression looks like this, and if we consider this as equation 1 and differentiating this equation with respect to IC, this will becomes like this, and we have to rearrange this equation when we are differentiating this equation with the IC for keeping this DIB and DIC in a left hand side, so that we will get minus of RE divided by RTH plus RE is what the expression that we got for DIB divided by DIC. So, DIB divided by DIC is the stability factor we already know, it is the rate of change of base current to the rate of change of collector current. So, this is the stability factor for a voltage divider circuit. So, finally, if we have that stability factor, that what we found is substituted for the formula S is equal to beta plus 1 into RTH plus RE divided by RE into beta plus 1 plus RTH. So, this is completely dependent on RTH, that is Thevenin resistor, and also the base that emitter resistor, that what we are already said, that emitter resistor is going to help in a stabilization. So, by rearranging this, again this expression can be rewritten like this. So, from this expression we can able to inference that S should be small. This is what from the basic concept of stability or stabilization that we know. S should be always lower for better performance or better stabilization. For S should be small, which can be achieved by making this RTH divided by RE should be always small, and also for RTH divided by, for very small RTH divided by RE, S is equal to 1, then that case is called as ideal case. Whenever RTH divided by RE is equal to 1, that case is called as ideal. And also another thing is, for very small RTH divided by RE, if R2 decreases, that RTH current, that is Thevenin current drawn by R2 will be large. So, this will be large enough. So, if RE increases, large VCC, that is supply required for that, hence compromise is made in selection. So, we need to compromise in selecting the resistor value, that is R1 and R2 resistor value, so that we can able to fix up this ratio RTH divided by RE, which has to be lower. So, if this value is small as possible, then we can able to get the stability factor also low value. So, finally, we come to the end of this session. In this session, we are concentrate on biasing and stabilization of a transistor, and also we studied about two different types of biasing scheme that is used in BJT transistor. So, biasing refers to the application of DC voltage to set up the operating point in such a way the output signal is undistorted throughout the whole operation. So, output should not be distorted when we are going to choose a DC supply voltage for into the transistor. And also the process of making operating point independent of temperature changes or variation in transistor parameter, that is known as stabilization. So, even this temperature will always leads to a different effect on the transistor, because the temperature is if they change the temperature, the collector current increases, because indirectly the leakage current is dependent on the temperature. If leakage current increases, obviously the collector current increases. So, we have to maintain the temperature in such a way that temperature should not affect the transistor operation. So, this can be achieved with the help of stabilization. And also two types of biasing scheme that we study. One is fixed bias, there are base resistor bias, another one is voltage divider. In fixed bias or base resistor bias scheme, a base resistor value will going to help in changing the Q point. So, that is the operating point can be easily changed by choosing the base resistor value. And also in voltage divider, in this form of biasing, R1 and R2 will have going to divide the supply voltage into two equal values. So, supply voltage will be divided equally with the R1 and R2. So, that is why it is called as voltage divider bias circuit. Here also we can able to find a better stabilization, and also the biasing also helpful here. This is the voltage divider bias scheme is more widely used than the fixed bias, because this scheme is having which will going to helpful in amplification properly, and also this scheme will be helpful in proper amplification, and also the transistor will stay in a linear or active region for long time. That is why it is used as a widely. In fixed bias, it is most commonly used in a logic gates application. Some of the questions of this session are: what is biasing of transistor? What is stabilization in a transistor? Which are the two types of biasing method used in transistor? So, references are www.allaboutscircuits.com and www.electronicstutorial.com. Textbook references are Electronic Devices and Circuit Theory by Robert Boylestad and Louis Nashelski, and also Electronic Circuits and Devices by Alan Mottersheed. This ends the session. Thank you.